Hello! Today we will be doing Equilibrium Part 2 calculations by Davina, Isaac, Robo, and your host for tonight, Cruz. Let's begin. What we'll be doing, two icebox problems, one with quadratic formula and another with shortcut method. Then we'll be doing two free energy problems, one free energy on pressure problem and another free energy and equilibrium. Icebox equilibrium problems. If you want to follow along, go flip over to Chapter 13 Exercises, pages 616 to 617. Problem 47 in the textbook, at 2,200 degrees Celsius, the constant equilibrium constant for pressure is equal to 0.05 for the reaction. What is the partial pressure of NO with N2 and O2 that were placed in a flask at the initial pressures of 0.8 and 0.2 atms respectively? So we know that the equilibrium constant for pressure is equal to 0.05 and the product is 2NO gas. Reactants are 2NO, 2N2 and O2. And we initially have 0.8 atm of N2 and 0.2 atm of O2. So we need to plug this into an icebox chart. So on the top, we're going to have to put in the reactants and products. And then we do our ICE. ICE stands for initial concentrations and equilibrium. Now, for ICE, we plug in the initial, of course, so it's 0.8 atm for N2, 0.2 atm for O2, and since there's nothing for NO, we just put in a 0. Change. How much is it going to change by? Well, it's going to change by how much the coefficient is. For reactants, you're going to subtract x because no cost. But for the products, you're going to have to add. So minus x for N2 minus x for O2 plus 2x for 2NO. Now, equilibrium, how much is it going to change by? Well, we'll just take our initial, and then we add or subtract by the change. So, 0.8 minus x, 0.2 minus x, and 2x. Now, how we're going to solve the partial pressure of NO with N2 and O2 at equilibrium? Well, we have to plug it into the equation. So, equilibrium constant for pressure is equal to the pressure of NO squared divided by the pressure of N2 times pressure of N2. Basically, products over reactants. Now, how do we know that NO is squared? Well, that's because the square is the coefficient of NO. Now, we plug in the equilibrium constant for pressure, and we also plug in it's going to be at our E values in the ICE box. Now, multiply the bottom over, and then simplify it, and subtract over to the 2x squared, simplify it, and we're left with 3.95x squared plus 0.005x minus 0.008 is equal to 0. Now, to find the x value, we have to put it into the quadratic formula because you can't really simplify it with just writing it out, and yeah, you're just gonna have to play it. So so the quadratic formula is x is equal to minus b plus or minus square root of b squared minus 4ac divided by 2a. A is the A, B, C are coefficients to x squared, x, and no x. So we plug that in, we get x is equal to 0.0443 and negative 0.0455. Since pressure or concentrations can't be negative, x must be 0.0443. Now we plug in the E values and we get the we get 0.7557 atm for PN2, the pressure of N2, 0.1557 atm for pressure of O2, and 0.0886 atm, the pressure of NO. Okay, now problem 53. At a particular temperature, the equilibrium constant is equal to 2 times 10 to the negative 6 for the reaction. If 2 moles of CO2 is initially placed into a 5-liter vessel, calculate the equilibrium concentration of all species. What we know, the equilibrium constant is equal to 2 times 10 to the negative 6. The reactant is 2 CO2, and the products are 2 CO and O2. And the initial is 0.4 molarity of CO2. Plug that into our icebox, and we get equilibrium values is 0.4 minus 2x, and x. Now, concentration is, so plug that in, concentration, and we get 2 times 10 to the negative 6 is equal to 2x squared times x divided by 0.4 minus 2x squared. We could, so, since the K value is really low, like really low, we can assume that x is equal to 0 because it's not going to change much, right? Because there's not much of change. So we're just left with 2 times 10 to the negative 6 is equal to 2x squared times x divided by 0.4 squared. We multiply it over, divide by 4, and then cube root it. We get x is equal to 4.31 times 10 to the negative third. Now we need to plug in the values for the equilibrium, and we get 0.39138 molarity for CO2, 0.00862 molarity for CO, and 4.31 times 10 to the negative third molarity for O2. Ain't that nice? Now, free energy. Now, if you want to follow along with this, you have to flip over to chapter 16, exercises, and pages 785 and 786. Now, problem 57. Using data from Appendix 4, calculate the delta G value for the reaction. For these conditions, T is equal to 298 K, P is pressure of NO is equal to 1 times 10 to the negative 6 atm, pressure of O3 is equal to 2 times 10 to the negative 6 atm, and pressure of NO2 is equal to 1 times 10 to the negative 7, pressure of O2 is equal to 1 times 10 to the negative 3 atm. Yep, that's a mouthful. Now, delta G of O is equal to products minus the the delta G values for the products minus the reactants. So we do that all, and we get, and then we look it up in our Appendix 4 values, all these values, for the products and reactants, subtract it, and we get negative 198 kilojoules per mole. Now, the Q value, it's kind of similar to the K value, except instead of the concentration value, the quotient is basically the value. Basically, the values we're given currently. Does that make any sense? Yeah, it makes sense. So the pressure of so like the K, we plug in the pressure of products divided by the pressure of the reactants, and we get 50. Cool. So now the total delta G is equal to the delta G per mole plus RT R times the temperature times the L times ln of Q. And after we plug that all in, we get negative 188.3 kilojoules. Now, problem 65. Consider the following reaction. Cool. We solved our reaction, by the way. Now, problem 65. Consider the following reaction at 800 Kelvin. An equilibrium mixture contains the following partial pressures. The partial of N2 is equal to 0.021 atm. Pressure of F2 is equal to 0.63 atm. And the pressure of NF3 is equal to 0.48 atm. Now we have to calculate the delta G of O for the reaction at 800 Kelvin. Now we solve it like we do. Equilibrium constant pressure is equal to products over reactants. Plug that in. We get 43,877. That's G of O. G of O is equal to RT ln K. And we plug. Oh yeah. R value is equal to 0.008314 kilojoules per mole per Kelvin. Temperature 800 Kelvin, and Kp, the equilibrium constant, is equal to 43,877, and we get negative 71.1 kilojoules per mole. And that would be ending our presentation. Thank you for watching.